Okay, thanks for the kind invitation to this meeting, and thanks Kronis for the very deep introduction about the mid-Pleistocene transition, and also for putting a lot of pressure on the ice core community for the next few years, or well, months actually. Well, let me start the timer here. Well, I'm going to speak about these extraordinary efforts that the ice core community is doing to retrieve an ice core at least as old as, well, hope 1.5 million years. So the answer has been already given by Kronis. Do we really need another deep ice core? And the answer is yes. We need a CO2 record extending as far as we can, hopefully to the mid-Pleistocene transition. And for those of you who are in an early career stage, I want to underline this extraordinary effort which has been done in the European project for ice coring in Antarctica. We celebrate this year the 20th anniversary of this iconic paper in EPICA, where we reconstructed the 11 interglacial cycle of the ice sheet, including the greenhouse gas record. So, but when we published this paper, we realized that we were exactly at the end of the mid-Pleistocene transition, a so important events that we already started to plan the future of the ice core. We realized that we definitely needed an ice core, and we know that there are many ways in which the climate community changes perception of is perception of climate, because with an ice core you can literally quantify climate forcing and response factor of climate. So to have on the same record the temperature, of course, and the forcing, like the dust and gases, is extremely important. Of course, you might also have the direct information from the interlinking between the carbon cycle and climate. And last but not least, and I think that Emily will deal about that with the short and the Rolos millennial transition, like Danska-Oeschger events, which are well covered into the ice. Well, so we know that as we have seen, the mid-Pleistocene transition is extremely important. It's extremely important to understand how the climate changed in the past and what is also happening today. So we are today living in a 100 kiloyear world, but before the mid-Pleistocene transition, which actually happened, as I told you, just before the record that we had with the EPICA project, we had a 40,000 kiloyear world in which we had a higher frequency and low amplitude of that, and that was before the mid-Pleistocene transition. And after that, we are living, and we are still living, into this 100 kiloyear world, dominated by very ample cycles, so it becomes more and more difficult to deglaciate, actually. So the things that happen, and you see here the limit of the ice core, so we can't say that much from this point of view. But what we can say is that it is also important for many other different reasons. It's not just a climatic transition, but there was this paper last year published on Science by a group of anthropologists that, well, they claim that something happened exactly well, the time scale goes from top to the bottom. It's totally reversal to what we are used to do. But there is this interesting paper that something happened in the mid-Pleistocene transition. For 100 kiloyear, the population of hominid went down to a few thousand, actually 1,280 people. Well, how they did that? Well, they used modeling of the genomic. Well, if it is hard to understand how climate modeling is working, this is even more difficult. But, well, it's constrained by observation. And, well, it happened, this bottleneck in our evolution, just in the middle of the mid-Pleistocene transition. So if you're here, it's just because we hold on that to these brave guys that 900,000 years ago resisted to this transition as well. Well, explanation, as we have seen, Kronis did a wide overview. I'm going very quickly. Is not linked to the orbital transition. Nothing happened, nothing significant happened, either in obliquity or in precession, modulated by eccentricity. And well, we see in the bottom panel the insolation during that period oscillate as let's say, business as usual. There are many hypotheses linked to the physical change. Again, I tell you, there are threshold mechanisms, as we have seen. The concept at the base of that is that it was more difficult to deglaciate. When you have a huge ice mass, it is very, very difficult to get rid of that. And above a certain threshold, we were in this condition. Then again, there are explanations that, as we have seen, are reconduct to the regolith hypothesis, to the fact that we have this silty and very slippery basement under the ice sheet, which make for a certain period of time easy to have a lower and less big ice sheet. And after the certain period, the mid-Pleistocene transition, the ice sheet went bigger and bigger. And then more recently, there is this interesting paper that has been published a few months ago with a new insight on the mid-Pleistocene transition, in which the role of Southern Ocean has been really highlighted. So there is a drop into the global mean surface temperature, pretty faster than it was before. Of course, the declining trend, as we have seen from Kronis' talk, has been constant, but with an acceleration during that period of time, which is also supported by CO2 record as far as we have. Of course, the continuous record is only available for ice core, from ice cores. Again, well, we need an ice core then. We need to have a continuous record covering as much as possible far back in time. And the only way we have is to go to Antarctica and to try to retrieve another deep ice core. And in fact, unless we understand the transition from the 40,000 kiloyears to the 100 kiloyear during the mid-Pleistocene transition, we can't say that we will understand completely the climate, and especially linked to the sensitivity of climate to greenhouse gas changes. So we also want to understand why we did have actually a mid-Pleistocene transition, why we didn't have it earlier than that, and so why also we live in a 100 kiloyear world today. So if you look at again, this is another way to put in the context what we have today with the record. As you see on the right, we have both the benthic record, the greenhouse gas, and the ice core record. And on the left is what we have about the greenhouse gas concentration, reconstructed by proxies like for instance, boron isotopes in other archives. So there is a big gap apart from few other ice core records that are coming from what we call fossil ice. In some region in Antarctica, we can go back in time 6 million years, but it's not a continuous record. And the greenhouse record is not well preserved in that. There are in places like Allan Hills. So we are seeking for oldest ice in Antarctica. There is a big, I wouldn't say context, but the big multinational program looking for oldest ice. As you see, there are the Japanese working in Dome Fuji, Dome F, the Chinese working in Dome A, the Russian working close to the Vostok station in Ridge B. There is we as a European consortium are working nearby the Concordia station in East Antarctica. The Australians are doing the same in the same place, and the Korean will do the same in a few years. So we need a deep ice core. We need a place where we have low accumulation, of course. We need a place which is cold, no melting at the base, in the interface in between the bedrock and the ice, but not too thick, because if it is too thick, we literally might have the melting, and of course lateral flow. And the blue dot that you see is where you can find oldest ice, not in a continuous record, but in this fossil ice that I told you before, up to 6 million years old ice. Well, so it's where we settled a few years ago. It was a project that started beyond EPICA, that goes beyond the European project of ice coring in Antarctica, started in 2019 actually, with a long time to convince the European Commission to go through a new ice core. But then we started to survey the area of Dome C. We went through more than 20,000 kilometers of radar line geological survey, and the fact that we had, for instance, radar line connecting the Epica core and with the reflection of the Epica core into the new site. So following the line, the radar line and the reflection, every glacial and interglacial could be followed. So then we had a numerical model to estimate the age of the deepest part of the ice. Of course, it takes into account many different parameters like the mechanical ice thickness, the average accumulation rate, and the thinning, of course, with the depth. These are the most recent results. We put new lights in the recent years. We started to drill actually on the selected site in 2021. These are a profile goes from Epica Dome C, the site where it is the previous record, and the new site that is called Little Dome C is 35 kilometers apart. And as you see, there is a modification on the flow line, and especially if you look on the right side, there is a bunch of ice. It's about 200 meters on the bottom, which is called stagnant ice. We don't have a clear reflection from the radar, so we don't literally see whether there is a climatic signal on that or whether it is, again, fossil ice, which is there since probably millions of years. We have models on the new lines. So we could compare the Epica Dome C core. We do also have data for that. We could compare the Dome F, the Japanese record, and of course we could model the Little Dome C. As you see, there are a deviation point from about 500,060 years in the Epica Dome C, in between the model and the real observation, also in Dome F. And this is the model that we have in Little Dome C, the most recent model in recent Dome C. So you can see that estimate at the bottom is less than we expected. So it's not 1.5 million years, but most likely at the top of this 200 meters of stagnant ice is 1.2 million. So this is more or less the three ice cores, the three sites that we have around Concordia. So you see on purple, you see the Epica Dome C core, which goes back in time 800,000 years, is the Epica record. We see the blue one, the site that we selected for our drilling, and I'll show you in a minute where we are, which most likely at the bottom, if you're lucky, will go from 1.2 to 1.5 million years old. And there is that new orange line, which came out very recently, actually. The paper is of the fall of last year, that model in what we call North Patch, which is about just 10 kilometers far from Concordia, a new record with a model age of about 2 million years. That would be the place, of course, but we didn't know 5 years ago when we started to drill. Well, so the adventure started for us, as I told you, in 2019. We are drilling in Little Dome C at this side. So we are aimed to retrieve a continuous record down to the bedrock. And basically, the most important things for us is to have a climatic signal, a high-resolution climatic signal for all this ice. Logistic is very heavy, is a multi-year international program, about 5,000 man-day in the field, cargo and ships and a lot of people and money involved. We are far away from the coast, 1,200 kilometers from the coast. I let you imagine all the logistic involved. We set up the camp in 2019, and the camp grew up. You can recognize the big tent with the drilling tent. We have an underground cold storage for the ice. We progressed quite well in the last few years. This is where we are. You see the progression from 2021, 22, 23, and 23, 24. We are at about, we are about at 1,800 meters deep. We have about 800 meters to go down to the stagnant ice and about 1,000 meters to go down to the bedrock. Next season will be crucial for us. We will be deployed in the field in a 1.5 months from now, and we hope to reach the bedrock next year. So we do have analysis in the field. We want to know where we are. So this is the Epica record on the bottom of the first 200,000 years, and on the top is the measurement we do on site. We want to know where we are while drilling. So we have delta O18 and delta deuterium analysis on site, and also other physical characterization of the core that tells us exactly where we are. Well, it took a while to split the cores. I mean, it took more than 9 years to decide how to split the cores. You see this mortadella slice, you know, I call it as a mortadella slice. We fight for 9 years how to split the core. We have a lot of new things coming out, but of course the climatic signal, including the chemistry, the stable isotopes, and the gas will be the most important. We are looking at many different parameters: the temperature, precipitation, greenhouse gas record, the proxy of sea ice, looking at bromine into the ice content, the weathering proxies like the CF4, and so on and so forth. And as Barbara showed yesterday, since the resolution of the ice core will be very, very little at the bottom, imagine that we will have about from 15 to 20,000 years in 1 meter of ice at the bottom. The oldest ice older than 700,000 years, will be squeezed in 200 meters. So we need very high resolution techniques. This is why we are developing a new technique with laser ablation. Scanning the ice is a non-destructive technique that allows us to go down to 30 micron resolution in the chemical signal, both for the chemical signal, and you see a map, a chemical imaging analysis of a 35 by 7 millimeter very tiny piece of ice. But well, we plan to apply that scanning all the ice, including what Barbara showed yesterday, the profile in the delta O18 and isotope. Just an advertisement at the very end about and again I'm addressed to the youngest generation of scientists, the new Italian National PhD program that Barbara and I are carrying out with different topics and so on. And I thank you for your attention.